Hello, my name is Jon NORDBY. I'm head of data science and machine learning at Soundsensing. We are an IoT sensor company that focuses on sound and machine learning. Today I'll be talking about environmental sound classification on microcontrollers. So environmental sounds are sounds that we have around us in our environment, especially outdoors. It can be car traffic, cars honking, music played from a club in the area, speech from loud goers, or construction site sounds. And when the environmental sounds are unwanted, we call this environmental noise. And environmental noise pollution is a big and growing problem. We live in very urban environments with more and more noise sources around us. The WHO estimates that in Europe alone, 13 million people suffer from sleep disturbance due to noise. Such noise, be it in the night or in the day, causes the body to be stressed and in constant alert mode. This increases the risk of cardiovascular disease, obesity, and so on. This means that almost 1 million disability-adjusted life years are lost due to noise alone, and makes environmental noise the environmental pollution that affects the most people in Europe and several other parts of the world. Another serious problem is hearing loss. It's estimated that 40 million people globally are affected by hearing loss from work. This affects workers from many industries, including construction, manufacturing, and shipping. Soundsensing helps to address these issues by providing better tools for monitoring noise, understanding the underlying causes, and what's needed to make improvements. We provide an easy-to-use IoT sensor that can continuously measure the noise level, as well as classify the dominant noise source over time. This is presented in the dashboard, and it's also available in an API. So when you want to make a noise monitoring or any kind of wireless audio sensing network like this, you have multiple system architectures to choose from. A conceptually simple model is that the sensor will record and transmit audio to the server. It's located centrally, and the server will classify the audio into the classes that you're interested in, do the analysis. However, this requires a lot of data to transfer the audio, and it also is very bad in terms of privacy, as potentially sensitive audio, such as speech, will be transmitted over a network and could potentially be stored at the server. However, it's very easy in terms of the compute constraints, because you can have large machines that run your machine learning model. An alternative could be to pre-process the audio into indicators that you would then transmit to the cloud and only classify this smaller compressed representation. This might be better in terms of privacy and data traffic, but it's hard to find a trade-off where the information needs to be rich enough to do the classification and the analysis that you are interested in without becoming a privacy problem. So this makes the tinyML case very interesting, where you perform all of the processing in the sensor itself, and you only transmit the classes of interest or the analysis results over to the server. This is the best in terms of privacy and also in terms of data traffic, which saves also energy on transmitting data. However, it means that the entire model needs to run on a small device, which is a challenge. Some typical constraints for a microcontroller-based device would be ARM Cortex-M4 from STM or others. And if you would dedicate 50% of the capacity to the machine learning alone, you would have 64 kilobytes of RAM, 512 kilobytes of flash, and 4.5 million operations per second. In 2019, we reviewed the existing models for this task on the Urban Sound 8K open dataset. And we show here in the green region the feasible area for the compute and storage capacities of a microcontroller device. And in the middle and top right, you have the existing models that are state-of-the-art. And we found that all models were outside the budget for both CPU and storage by 1 to 2 and sometimes 3 orders of magnitude. We also showed in the same paper that it is possible to classify environmental noise within this device budget. And we are able to do this at the time with approximately 10 percentage points from the unconstrained state-of-the-art. We've seen several improvements to close this gap further, but these are not published. So as far as we know, this is still the best published results on the Urban Sound 8K for this kind of device constraints. So how did we do it? How do we make these networks run on such small device? To review the typical audio machine learning pipeline, the top, you have the input, the audio signal from a microphone. It is chopped into fixed length windows. Each window is passed to a feature extractor, typically to compute a spectrogram, typically a MEL spectrogram. And then each MEL spectrogram is passed to your model, typically a convolutional neural network, could also be a recurrent neural network. And then this outputs probabilities for each of your classes. And if you have classes which are longer than a single window duration, then you aggregate these predictions over time to make the final prediction. So how do we optimize the various parts of this system? So one important thing is at the start, in the pre-processing phase. Reducing the input dimensionality that goes to the model, that is the output of the pre-processing, is very important. One can reduce the sample rate. One can reduce the length of the window seen by the model each step. One can reduce the frequency range that is covered. For example, if you're not interested in super high frequency, you can drop it. And you can reduce the frequency resolution. To combine this, you can get up to 10x reduction in compute. And because the input complexity is now lower, it can also be easier to learn for small data sets. Also important is to reduce how often your model is executed. So the windows are typically made with overlap. So a new window has mostly part of an old window, and existing models have maximum overlap. So they sometimes classify essentially the same piece of audio up to 20 times, which is a huge reduction in inference performance. However, often there is a small performance benefit to this. So you can use either no overlap or 50% overlap or maybe 25% overlap and get most of the performance. And of course, it's important to use a small model. If you would compare this to images, the models that you need for effective audio tasks is actually quite small. Typically, you get very far with 2 to 4 convolutional layers, followed by a couple of dense layers on many tasks. And while there are works that show you can start with a big model and then prune to get down to a small one, we found it very effective and much easier to simply start with a small model from the start. The convolutions are the most compute requiring operations in the convolutional neural network. And a 2D convolution actually does convolutions over 3 dimensions, the 2 spatial dimensions, the width and height, and also the channel dimension. And this can be separated into 2 operations. First, a convolution over the height and width, the spatial dimensions, with a depthwise convolution, and then a pointwise convolution, which is only over the channels. And this can, depending on your filter configuration, can give you 5 to 10x speed up. Another area where you can improve is to avoid max pooling. So with max pooling, the convolutions have typically computed some outputs next to each other, and the max pooling operation that follows picks only one out of the input window as its output result. This means that 3/4 or sometimes more of the results is actually discarded, which is very inefficient. Instead, you can downsample by using a strided convolution, which means that the convolution operation actually moves over by 2 or 3 or more instead of over by 1. And this effectively downsamples in the same step, which can actually perform better than max pooling because the downsampling is also learned, and approximately 4 times speed up. Towards the end, one should apply quantization. Many works have shown that integer 8-bit can perform nearly as well or equivalent to floating point full precision. And this gives a 4x improvement in the weights that you use in your flash memory and your activation, which you need in your RAM. And in the ARM Cortex M4 and similar CPUs, you can get 4x or more improvement by using the SIMD instructions as well. Of course, there are many more techniques that you can apply that are more specialized. This is only a start. And many of these are covered in dedicated talks here at tinyML Summit. For example, binary network quantization, neural architecture searches, streaming inference, and hardware acceleration. So what does this give us when we're able to run these networks on the device? So our customers use sensors with this automated classification to create an automatic logbook of noisy training activities. One of our customers operates a training facility for police special forces, where they fire guns and conduct explosive training, which is, of course, quite noisy. And they have restrictions on when they can do this. And they use our system to have documentation that they follow these regulations and to verify any noise complaints. And we are now expanding the solution to other applications, such as construction, industry, and transportation. So if you're interested in these areas and have tests, please let us know. We have also used these techniques to develop anomaly detection with using sound, which we've tested successfully on pumps. And this frees up janitor time and better monitors the condition of technical machinery. So in conclusion, we can classify audio environmental noise directly on a sensor. This is made possible by applying a range of efficient convolutional neural network techniques. And this has been integrated into sound-sensing IoT sensors, and it can be used for noise monitoring as well as condition monitoring. And we are open for partners and pilot projects around this. Any questions?
So if you do have a question, just go ahead and go off mute and ask it. Jon, I have a question. You mentioned CMSysNN. Is that the software stack that you guys are using for inference?
We use primarily the STM X-Cube AI package from ST Microelectronics, and I believe that they use CMSysNN under the hood as the accelerator package, which is also used by TensorFlow Lite and many other packages.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute, Lattice Semiconductor, gold sponsors, BrainChip, Babel Labs, DSP Group, Edge Impulse, EMSA, Gray Matter Labs, Greenwaves, Hymax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.